All right, so welcome to theme 2. And so in theme 2, we're looking at investigations of the lunar surface, which cover a wide variety of things, which you're going to see. And my name is Maria Banks, and so I'm the lead of this theme of our TREX group. So I mean, essentially, the moon is the only solar system body, as we all know, that humans have visited. And very hopefully, likely, it will be our next or a future human destination. So in this theme, we aim to characterize many different things, including lunar grain size, mineralogy, different kinds of thermal attributes and space weathering effects. And we're also going to talk a little bit about high priority geologic features. And all of these investigations have an overall goal of addressing ISRU, future instrument development needs, and of course, also informing future human and robotic lunar surface exploration. And as Deborah said so well, you'll see how we're trying to tie in different aspects of the other themes, and then also use our work here to inform the other themes, especially theme 4, which Elda will be talking about in a little bit. And I have, just as Deborah did, I've asked each of the speakers to put together an initial slide with a picture of themselves and a little something about themselves. I wanted them to talk about some of the other roles they play in research and exploration that are very complementary to our TREX work here, including any mission involvement, work they do with CLIPS and Artemis, and other scientific investigations and field work. And of course, collaborations they have with across Survey and other institutions. And basically just want to show off the amazing diversity of our team and how each of them brings unique expertise in many areas of science, exploration, and relationships across the world and across the field to benefit our team. And I'm really proud of our team, and I think they do a great job. So let's move on to Amy, who's going to talk first about simulating the impact-induced mixing of olivine on the lunar surface. Go ahead, Amy, please.
Okay, can you guys hear me?
Yes.
Okay, thanks. Well, greetings from Europe, where it's very dark and very cold. So I want to talk about some work that I've been doing for a while with Ed Rivera-Valentin, who's at LPI in Houston, Texas. So Ed was my postdoc, and we developed a code. I'm going to be talking to you about this code and how we're going to apply it to the moon. Ed and I are kind of interlopers when it comes to lunar studies. Both of us typically are inhabiting the outer solar system. But anyway, we enjoy the moon just as much as anybody else. Let's go to the next slide. Okay, so I want to talk a little bit about the process of impact-induced mixing. This is on the right-hand side of the slide. You see a schematic of this process. So when an object hits the surface of a solid planet, that's the blue circle is a sort of notional impactor. The impact itself and the excavation of the crater throws material from the subsurface up onto the surface. So on the upper part of this diagram, you see that if you hit a layered planet that has a gray crust and a sort of greenish mantle, if you hit a layered planet with a small object or something that's not going very fast, you're just going to take crustal material from the subsurface and deposit it onto the surface. But if you hit a layered planet with an object that's larger or something that's going really fast, you could potentially pierce all the way through to the mantle and basically excavate mantle material up onto the surface. So what's interesting about this is that if you simulate this process, the locations of the sort of mantle material on the surface of the planet and the amounts of mantle material that you find can tell you something about the initial thickness of that crust on that planet. So this is something that Ed and I studied for the planet Mercury in a couple of papers that came out a few years ago. And so, when the opportunity to work with the TREX team came up, we thought, well, it would be really interesting to take this model and apply it to the moon. So let's go to the next slide. So what followed was several years of very painful software development. The reason being that we originally wrote this model in IDL because, to be honest, we were lazy. And if you really want to do a good job of simulating impact-induced excavation of, you know, a layered planet, you want to be able to do it in very high resolution. So you want to be able to have many, many elements that span the crust. And in the case of the moon, where the initial crustal thickness is sort of 100-ish kilometers, you want to be able to have, you know, 100 or so elements spanning the crust. Unfortunately, we ran up against, you know, the inherent limitations of IDL. It's not intended to do things like this. And so we've spent the last many months porting this code into C. And so now we're finished. What you're seeing here is a 3D planet, a fully 3D planet. The reason why it looks bumpy is that it's a 3D planet made of cubical blocks. So you can think of it as a planet made out of Legos, but it's a sphere. And what the colors are is that's telling you the volume fraction of the surface of the moon that is composed of olivine. This is a moon with an initially 20-kilometer thick crust that's been subjected to a bombardment consistent with what we think happened in the first sort of 500 million years of you know, the dynamical evolution of the solar system. So it underwent sort of a two-phase late heavy bombardment. And so let's go to the next slide. This is what happens, just to give you an idea of what happens when the crust is thicker. So on the left-hand side, I believe that's a 40-kilometer thick crust initially, and on the right-hand side, that's a 60-kilometer thick crust. So what you can see is that the amount of olivine or mantle material, however you want to view it, that ends up deposited on the surface depends a lot on that initial crustal thickness. Let's go to the next slide. Okay, so part of the reason why I wanted to talk about this model is that, you know, here we have this really interesting numerical method, and what we would like to do is to reach out to other members of the team and talk about different ways that this could be used to answer different scientific questions. So obviously we have some kind of idea of what the initial crustal thickness was for the moon. But what this model can tell you, in addition to, you know, answering that kind of question, is it can tell you, for example, you know, the provenance of the ejecta material. So if you have a crater with some sort of volume fraction of olivine or some different type of material, you know, where did that material come from initially? It can also help inform exploration strategy, because, you know, you can imagine if you want to ask a question, you know, where would I go on the moon if I wanted to find, you know, have the highest probability of finding stuff from the deep subsurface? You know, you may think that you know the answer, but, you know, due to all of the, you know, sort of subsequent, you know, impacts, like, you know, you have an impact and then you have an impact onto an ejecta blanket and so forth and so on, the answer may not actually be so obvious. And so the interesting thing about these numbers of these volume fractions of mantle material or whatever is that also represents the probability of finding a rock from the mantle in a given location on the surface. So this could help us understand, you know, where are the best places to go to look for material that we think really came from depth. So we're in the process of basically finding more computing power so that we can really get a lot of resolution across these upper layers of the moon. And also, you know, in the process of reaching out to other people on the TREX team to see how this tool might be used. And so, you know, we're really interested in working with spectroscopists who, you know, have good knowledge of, you know, where the mantle materials are found on the moon and so forth, and, you know, using that to compare our model outcomes, and also thinking about talking to people about exploration strategy and how our model can inform that as well. So that's a little update on where we are.
Cool.
Thank you, Amy. Go ahead, Amanda. Let's go to the next slide.
Okay.
Okay, so I'll take this one. So my name is, as you know, is Maria Banks. I'm at NASA Goddard Space Flight Center. And in addition to Theme 2, I also work with Theme 4, and looking forward to when we get to go out into the field. That's okay. But I bring to the table at TREX, you know, some experience with several missions, and also LRO, where I'm the associate project scientist for land admission support and science data management, which means I get to coordinate the communication and image requests between CLIPS and the instrument teams, and also having a lot of fun working on a couple of Artemis working groups. Okay, go ahead, next slide. Thank you. Okay, so I'm going to talk about several investigations, or actually I'm going to hand it off to some colleagues, but we're collectively talking about several investigations looking at young structures on the moon, in particular young tectonic structures called lobate scarps. And you can see there's a nice list of collaborators here, both within TREX and outside of TREX, and several in different survey nodes. So lots of collaboration and bringing in lots of different institutions, which is really nice. Everybody contributes a unique perspective and expertise. Next slide, please. Okay, so I have a lot of information on these slides because I wanted them to stand alone. And so I invite you to please take a look at these slides. If you're interested in more details, I'm just going to talk quickly about some of the highlights on each of them. And of course, let me know if you have questions. But first of all, lobate scarps, what are those? They're tectonic landforms. They appear as curving lobate cliffs. They're formed by compressional forces. They're very widely distributed on the moon, and we see them both in Mare basins and in the highlands. Next slide. And so one thing I wanted to definitely emphasize is that they're unique in that we think they're very young, among perhaps the youngest lunar landforms, and some may still be currently active today. And so there's several lines of evidence that point towards this, including crater size frequency distributions, which have showed that most of the studied scarps, or at least were active, most recently in the late Copernican within the last 400 million years. And also very interestingly, that showed some surface renewal and disturbance a few kilometers on either side of the scarp trace, indicating that materials are being redistributed, moved around, refreshed, filling in some cases wiping out small craters. Next slide. So this is a map of some of the more prominent lobate scarps, and I wanted to bring to your attention these blue dots. And so these are revised epicenter locations for some of the shallow moonquakes detected by the Apollo seismometers. And a recent study, Waters et al. 2019, worked with revising these epicenters and actually connected some of them to these lobate scarp thrust faults, just showing some additional persuasive evidence that they have been active recently, and even within just the 8 years that those seismometers were active. Next slide, please. And you may be wondering, how important is this? Are we really going to even go anywhere near a lobate scarp? Well, the answer is Apollo 17, of course, the astronauts drove right over the cliff face of the Lee Lincoln Scarp. And this is just one example of a scarp within a few degrees of the South Pole. And you can see it's located within a few kilometers of a PSR, a permanently shadowed region, which is outlined in orange. So it's very likely we will be working in areas that are in close proximity to these lobate scarps. Next slide, please. So the motivation behind our investigations is to understand these as unique structures of scientific interest. May they have some benefit for future exploration? Could they host resources in these freshly redistributed particles? And also, importantly, could they possibly pose hazards? Next slide, please. So I'm going to talk here really quickly now about do these lobate scarps pose potential hazards and what we're doing to take a look at that. So our team is exploring the application of what's called a probabilistic seismic hazard assessment, or PSHA. And so this is widely used on the Earth to understand the frequency and severity of earthquakes, the severity of ground shaking, and also is used to inform a range of engineering decisions, which is good to understand. And so now, for the first time, we can blend both our Apollo era and LRO data, along with new technologies and modeling, to provide the building blocks necessary to construct this PSHA for the moon. Next slide, please. So I'm going to talk very quickly through the PSHA components. Next slide, please. So there's a seismic source model, which characterizes the potential locations and characteristics of seismic events, as well as the rates of occurrence. Next, please. The ground motion model predicts ground motion as a function of earthquake magnitude, source to site distance, and etc. Next slide, please. And then last but not least, the seismic response model, which incorporates the effect of local site characteristics, the geology, the topography, and how that can affect ground motion at the site. Next, please. So let's look first at the seismic source model. So as I mentioned, we have ground motion data that was recorded from 28 shallow moonquakes by the Apollo seismic stations. Next slide, please. So we can use the estimated epicenters and magnitudes of these events to develop a preliminary magnitude reoccurrence relationship. And then we can combine this with our maps of lobate scarp locations to understand the potential distribution of shallow moonquakes across the surface. Next slide, please. So we're also exploring physically and statistically robust strategies to attribute this global seismicity and productivity. And so on the right-hand side here, we're showing some alternate surface solutions for shallow moonquake epicenters, along with a gridded representation of the moonquake potential, in this case, reflected by the number of faults per cell. Next slide, please. And then for our ground motion model, we are exploring high fidelity numerical models coupled with our measurements of fault characteristics and lunar topography to model the ground motion. Next slide, please. And as you would imagine, we need a large number of simulations needed to accurately simulate that ground motion. So to do this more cost effectively, time effectively, we are exploring machine learning derived surrogate models, and we're using them to build response functions that can emulate these complex numerical models. Next slide, please. And finally, we can use the data from the moonquakes recorded by the seismic stations to give us information about the shear wave velocity of layers in the near surface. So we're going to be using that to develop our site response component. And this information, of course, is particularly relevant for locations where local topography could cause ground motion amplification, in particular basins. And I threw on the right-hand side here a reminder of that location of a scarp. Many scarps are located within or nearby craters, which could act as a basin and have some ground motion amplification. So altogether, these approaches will inform future surface exploration, providing some insight, information regarding potential seismic hazards, and then also, very importantly, identifying information gaps and needs that can be addressed through that surface, through future surface investigations. Next slide, please. So now I'm going to turn this over to my colleagues who are going to talk about other ways that they're looking at other features on other areas and features on the moon, including lobate scarps, and looking at physical and compositional properties of the regolith and how these characteristics may differ locally and regionally. And so Jay, you're up next. Tag, you're it.
Tag, I'm it. Hi, I'm back. Hi, I'm Grier. I'm laughing at my slide because apparently I have 3 axes of involvement with TREX survey node because I can't spell. The 3 axes of involvement. I'm a scientist for theme 2, where I do studies of the optical maturity parameter of the lunar surface, supporting the lobate scarp, hazard resource, and grain size investigations. I obviously am part of the public engagement program, and I just talked about the workshop for disabled writers, as well as doing other SciComm opportunities. I'm also the survey focus group lead for the equity, diversion, and inclusion focus group. And I'm also engaged in some other EDI opportunities and work as well. So synergistic activities, I'm the first author of a science trade book called Airless Bodies of the Inner Solar System. I only have the one other author who's also associated with SERPI, and that's Andy Rivkin. I've been doing OMAT research for forever. Well, since it existed, and that's been in conjunction with lots of folks, but one of them is through LDAP via Angela Stickle PI. I have a past life where I was an isotope geochemist doing argon-argon dating. So that, in conjunction with the reflectance spectra and multispectral analysis stuff that I do, I've been part of the PCMS geochronology team via Barbara Cohen. And I do science and art and poetry. I'm a member of the Queers and Planetary Science group, and looking at the EDI white papers. And so those are some of my other activities that I've been involved in. Next, please. Right. Okay. So this is my slide for optical maturity parameter 101. I mean, it's a straightforward concept in a sense, built on the idea that you can look at bands in the vis and in the near IR. In this case, for the moon with the Clementine data, we were using the 750 and 950 nanometer bands. And Paul Lucy developed this approach whereby he correlated the those reflected spectral points in 950 and 750 space against the FEO content and maturity indices that were measured in actual samples from Apollo. So this parameter is calibrated by ground truth. So it allows us to sort of see past albedo differences and even a number of compositional differences. And given the algorithm of Lamelin, we can also take into consideration certain other geophysical parameters like the topography and other issues. So as an example, there at the bottom, there's a visible light image and an OMAT image of the same portion of the moon. And you can see a contact region between the highlands and mare and the difference in how the fresh young craters with immature ejecta pop right out. Next slide, please. Right, so following right on to what Maria was just talking about, one of the key things that I've been working on is the optical maturity studies of the scarps and ridges. And right there is the image of Lee Lincoln, which on we have the albedo on the left and then the OMAT image on the right. And I was very surprised when I started doing this work because we would expect sharp slopes. I'm okay. Could you mute microphones for me, Amanda? Thanks. So I mean, I was really surprised when I saw this image because we would expect the edges of something like a slope or a scarp to be constantly refreshing around it or at the top of it with immature materials. And there is just no signature of Lincoln in this picture. I mean, you could barely spot it in the OMAT image, and that's including if I go right in there and stretch that like crazy. So I was very surprised. And so we looked at a number of these features. We're seeing a case where some of them have optical maturity brightness, some of them don't. And then there's some with very complex relationships where the lobate scarps and the wrinkle ridges are connected with one another. And we're seeing some kind of association that's really fascinating. So we're diving into this data to see what that means. But I strongly suspect in relationship to what Maria was talking about seismically, that the processes that are erasing the small impact craters around these lobate scarps are also gently mixing or comminuting the soil and such that they're driving the maturity signature towards saturation at background levels. So this is directly then related to these ideas of the seismic investigations. And you can look for more directly related to that because we're going to be presenting a poster at AGU on December 14th. Next slide, please. Right. So that's only one aspect of what we've been doing related to optical maturity. I think the big thing, of course, is integrating all of these data sets because we have people obviously in all these different themes, and TREX is taking a really comprehensive look at all of these processes that interrelate on the lunar surface that are of a particular interest to landing site considerations and human and robotic exploration. And it's not just, for instance, something like hazards, it's also the resources, the dust, mixing, the vibration issues we talked about, and then composition, roughness. So, you know, we're interested in things like roughness related to optical maturity. Is that someplace that volatiles are being sequestered? Is that someplace that dust is pulling? The vibration and mixing, we've known for a long time that places like, well, I'll start with Jay Malash talked about the idea of acoustic fluidization way back in the day. And that idea that if you have vibration, you can get landslides to run out at much greater volumes and further and faster than you otherwise would have noticed. If you're in a situation like you're on the moon or on a coherent asteroid body, they don't attenuate the seismic waves anything like they do on the Earth. Those bodies, the moon rings like a bell once it's been struck. And so if you have movement along the fault line of a scarp, like a lobate scarp, and that means you're striking the bell, the area around it could vibrate in such a way that you would fluidize the regolith. And that's something that's been, I saw in Richardson 2019, where they confirmed some of that idea on asteroids. So it's not at all a surprise that we'd see it on the moon, particularly going back to what Maria said about how some features on the moon, particularly bowl or basin shaped features, can focus seismic waves. So we're kind of taking a look at how all of this plays together, not just in terms of the near side. I've got a topographic map there. There's an optical maturity map there. And then there's a grain size image on the lower right. Also taking a look at things that Ryan Watkins has done, looking at boulder counts and block counts around impact craters, which are really, really important from my perspective, because I can get ages for some of those craters, actual radiometric ages, and attempt to calibrate these things and figure out how this, quantify the change with time. So next slide, I think, is the last slide, unless this is the last slide. Yes, it is. So I'll finish by just saying thanks also to vortices and geodes with whom we have been working. Bye.
Okay. Great.
Next slide, please, Amanda.
Okay.
Ryan, are you available?
I am here, yes.
Okay.
I will give you a heads up that my children are going to wake up at any second. So if we have any guest appearances, don't be surprised. All right, yeah, so I think most of you know me, but I'm Ryan Watkins. You can kind of see my multiple hats listed here. I am on the executive committee for League. I help run the Next Gen group, serve on Blue Origin Science Advisory Board, do a lot of EDI work, volunteer with Mothers in Science, and somehow manage to do some research in the middle of all of that. So I do a few different things that complement TREX. The primary one being just photometric investigations of various lunar features. And so that's what I'll talk about on kind of the next few slides. So you can go to the next slide. All right, so photometry, if anyone doesn't know or isn't convinced yet, it's a very valuable tool for assessing the physical and compositional properties of lunar regolith. So there are a lot of different factors that affect how a surface scatters light, from composition to glass content to grain size, et cetera. And so as part of TREX, and just kind of my life in general, I use LROC imagery to look at photometric values across the lunar surface. So the LROC imagery gives us the orbital data necessary for photometric studies by giving us repeat imaging at different illumination conditions. And when we couple LROC NAC images, which are the high resolution, meter per pixel or better images of the moon, when we couple those with digital terrain models and HAPKI photometric modeling, we can determine photometric parameters at the meter scale and really get some neat information about the surface. So here in the box, which I'm pointing at, but I'm remembering you can't actually see me pointing, so sorry. But anyway, so three important parameters in the HAPKI model that you'll see on the next few slides are single scattering albedo, which is largely dependent on composition, and then B and C, which are largely dependent on physical properties. So that's kind of in a nutshell what you need to know going forward to the next slide. So real quick, more background on photometry. So basically, again, because you'll see this in the next few slides, what we do is we take, again, our NAC images coupled with the DTM, and this allows us to derive local viewing geometries for each pixel. And then these are plugged into the HAPKI model, and this spits out these parameter maps that tell us a lot about. So the one here is single scattering albedo, and it shows variations in composition across an area. And then we also B and C maps that show variations in physical properties. So that was the really dumbed down version. But go ahead and go on to the next slide. So a couple of things that we're doing as part of TREX. One is looking at the Apennine Bench Formation. This is an area in Imbrium that likely represents the only large province of exposed creep basalts on the lunar surface. This work is largely being led by Sarah Valencia at Goddard, but I'm helping her with some photometry, and you can see on the left there some single scattering albedo maps of the area, and we're using relationships between single scattering albedo and composition to kind of back out some compositional properties of this area. And this is a lot of work, going back to a lot of work I had done with Apollo data. So kind of the big conclusion so far, again, this is a work in progress, is that so far LROC photometry and M-Cube spectral data seem to reflect the composition and mineralogy that occurs in Apollo 15 creep basalts, thereby lending support that this area is likely this large province of exposed creep materials. All right, next slide. So this project started off as photometry, and then the photometry was actually somewhat unremarkable, but it was still worth discussing because it's really neat. So we looked at these thorium hotspots in the South Pole Aitken Basin. Dan Moriarty is kind of largely leading this effort. And so again, once the photometry was unremarkable, we turned to M-cube spectral data. So that's kind of where the meat of this project is. But basically kind of the 3 bullet points you see there are the main highlights from the paper that he's got coming out soon. In short, we've seen that the thorium distribution in SPA is consistent with a mantle-derived ejecta that's been later kind of obscured by subsequent geologic events and impacts. And these thorium-bearing materials exhibit this gabbro-neritic composition that is consistent with globally distributed late lunar magma ocean cumulates. But here in yellow is really kind of the big highlight from this work is that, given the thorium-bearing materials and then the impact melt compositions, we actually see evidence for stratification in the upper mantle at the time of formation. So this really gives a lot of insight into the origin of these thorium anomalies, which have been kind of debated over the years. So again, stay tuned for that paper. It will be out really soon. It's a really neat paper with some really neat data. So moving on. Okay, I'm going to kind of wrap it back into what Maria talked about a few minutes ago, looking at lobate scarps. So we've been taking a photometry approach to looking at these. Here you can see a lobate scarp at Henderson. We've got single scattering albedo maps and then B and C maps. The single scattering albedo maps don't show really any variation between the scarps and the surroundings, which is not surprising, so no changes in composition. But we've been looking at how the B and C values change. So especially if you look at the B map there, we actually see an abrupt variation in these values in very close proximity to the scarp face, and then kind of consistent background values that are different beyond the scarp face margins. Go on to the next slide real quick. This will be a kind of a quick slide change to just showing another scarp that has the same kind of evidence for these distinct values on the scarp face, but then different background values. And the next slide. And then we looked at this cluster of lobate scarps at Vitello, which were identified to be within about 30 kilometers of a shallow moonquake epicenter. And here we see distinct B and C values not only on the scarp face, but also dispersed on the surfaces surrounding the scarp. So this variation in these materials kind of beyond the scarp face may be a result of recent seismic shaking from slip events on the fault. Recent as in like within the last 50 years. And it could be that the other scarps we looked at didn't experience the seismic activity quite as recently. Again, this is kind of something we're still investigating. All right, next slide. So just kind of to wrap it up with the photometry, especially of the scarps, looking at these differences in B and C values, we may be seeing differences in physical properties and maybe even maturity between materials on the scarp and the surroundings. And this could reflect of the effects of seismic shaking from slip events. So these might cause changes in grain size, roughness, fine scale structure, et cetera. So our ongoing work is to apply these photometric methods to other lobate scarps and tectonic features, and then other landforms that may be relevant to this study. And just to kind of conclude the whole, I guess, lunar section here, because I think this is the last slide in our slide deck. This is just really just a small part of an approach to integrating different methods and data sets to inform surface properties and support future human and robotic exploration. And that is all I had. I'm pretty sure, again, that was the last slide.
That was the last slide. Thank you, Ryan. Thank you, Jay. Go ahead, Amanda, next slide. Okay, I want to introduce to you Tom, who we've heard from a bit today, but go ahead, Tom. Tom is going to talk about hydrogen and the lunar regolith from lunar spectroscopy.
Okay, so can you hear me?
Yes.
Okay, great. So I'll just introduce myself now. So I'm Tom Prettyman. I'm working on a variety of planetary projects. I'm involved in themes 2 through 4, as well as education and public outreach on TREX. We're working on Ceres data analysis and also development of detectors and archiving. I'm involved in several missions, most recently Psyche and LUNA but I've also was involved from beginning to end in the Dawn mission as the lead for the gamma ray neutron detector. Collaborators from all over. This talk I'm going to mostly focus on my work on the nuclear spectroscopy, and it's going to circle back to start to include other data sets and more collaborators. So let's go to the first chart. chart 0. So this is just an introductory chart. At the top, I have a question mark. This is the side of the moon that's facing Earth. And you can see the Procellarum creep terrain, and it's all red. And what that is the distribution of hydrogen away from the poles. And when you solve for hydrogen using the neutron data that we get from Lunar Prospector, you get this, this bright spot on the front part of the moon where you have a lot of hydrogen. None of us who work on Lunar Prospector believe that's what's going on. And I'm going to show you that for the most part, it's not. Next chart. So part of this work is to map a regolith composition. We use a couple different data sources. Lunar Prospector, this is really nice. There's a low altitude data set that's 2-degree equal area pixels that's underutilized. And so we're working with that. We also have recently archived with the lead of Dr. Yuki Yamashita, all of the Kagoya gamma ray spectrometer data. So that's available to us to work with as well. The principle of gamma ray and neutron spectrometry is shown in panel A on the right. And basically you have cosmic rays coming in. They make secondary particles. The secondary particles produce gamma rays. And both the gamma rays and neutrons that escape into space provide a fingerprint of what's in the surface from the standpoint of elemental composition. Far right, the data sets that we really love to work with, we can actually solve for 10 elements and get quantitative results for them on the spatial scale sampled by Lunar Prospector by kind of a least square spectral mixing approach where we're looking across all energies. So it's a really nice data set. Next. So this is a technique that we've been working on for a while. It's called N-member spectral unmixing. And this unlocks for us this higher resolution elemental data set. So basically what happens if you look on the left, I'm making a plot of iron oxide versus thorium, and you get this kind of triangular shape for the lunar sample data. If you try and fit all the parameters to the data, it's a mess. You end up with really crummy precision. However, with the nuclear spectroscopy data, you can do a really, really good job fitting the spectra with just 4 N members that contain all elements. That's on the right. And when you do that, the precision of the analysis is vastly improved, and you don't really lose any accuracy. And the N members that I'm using are shown on the right. N member 0 looks a lot like titanium. N member 1 looks a lot like iron. And N member 2, that's like aluminum. And N member 3, that's your thorium, uranium, and potassium. So you put all those together in a linear mixing model, and that does a really nice job fitting the gamma ray spectra. So one of the problems we've had, get a 3, please, is trying to figure out how to use the elemental information that we do have, how to use the nuclear spectroscopy we have to actually derive the concentration of hydrogen across the lunar surface. And we have this formula, which is in the top right, which says that the concentration of hydrogen is equal to a calibration constant K times the quantity of some C0 parameter divided by C minus 1. And C0 is a reference count. It's the count that you would have if the material you were looking at was completely free of hydrogen. And C is the epithermal neutron count rate that you observe, okay? So, well, there are places on the moon that are probably relatively free of hydrogen, so we can find those locations. But the problem is that C0, we found out, depends on the composition of the major elements and some of the trace elements in the surface. And so what we've done, we had initially started out with a very ad hoc method of solving this problem. And it frankly does not work. Now we found out what works. And namely, what we can do is we can use our spectral N-member mixing model and to derive for each of the N members what those parameters K and C naught are. And it turns out for any point on the lunar surface, you can just use linear mixing of those N members to figure out what those constants are. And then you can go in and solve for hydrogen. It's beautiful. Next. So there you go. So on the top you have before, and the bottom you have after. On the top you see, you can kind of see the polar hydrogen. It's in red. And then you see this horrible blemish in the middle, which is the creep terrain, which was analyzed incorrectly, assuming the parameters for determining hydrogen are constant. And then when we use the end member unmixing method, that blemish disappears for the most part. And now we're at the point where we've proven this technique. And one conclusion is that what's in the PKT isn't endogenic. Likely what you're looking at is some sort of exogenic contribution. So the prospects for endogenic materials being associated with creep is diminished. And we're now ready to circle back to the interpretation, where we'll be able to bring in parameters like OMAT, as has been done for the highlands, and write our paper. Last slide. And now it's time for T. So we are a toolbox project. We may as well have a toolkit to go in the toolbox. So we are developing T, which is Toolkit for Elemental Analysis. There's an example on the right where we provide an analysis for a small region. This is Moscow Vients, and you can see the end members and then the cumulative analysis that you have in the box. So next steps are to finish up our lunar hydrogen mapping study, working on a paper. As I said, we're circling back to interpretation now. And then we want to archive the revised hydrogen maps. And then we also want to follow that on to investigate small basalt units with our T toolkit. That's it.
Thank you so much, Tom. Amanda, let's go ahead and move to the next slide.
Okay.
All right, I'd like to introduce Amanda. Amanda is going to talk about using LAMP to look at water across the lunar surface. Go ahead, Amanda.
Okay, great. Can everybody hear me?
I can hear you.
Okay, great. Okay, so this is using Lunar Reconnaissance Orbiter Lyman Alpha Mapping Project, the FUV spectrograph on LRO to look at water on the moon. And we had a paper out about this. We had a couple of papers, but the most recent was last year. Some of you have heard some of this stuff, but we have made some developments since that paper, and we're continuing to do that. So I wanted to share this. This is all hinging on this water absorption edge that is very strong, and it is at about 165 nanometers. So this is in the far UV, and it's a strong absorption. It's actually, in terms of absorption coefficient, much stronger than even the 3 micron band. That being said, and we also don't have to worry about thermal corrections. That being said, as I mentioned even earlier today, far UV signals and the solar output is quite low in the far UV. And so signal to noise is always an issue. And so these results that I'm showing you are a culmination of years worth of LRO LAMP data to build up signal and study how water is varying across the surface and diurnally. So what we're doing is trying to measure spectral slopes across the surface in reflectance spectra, and looking for changes, especially in this area right in here. We're using 164 to 173 nanometers, where any spectral slope changes due to the presence of water ought to be strongest, and where we might expect to see diurnal variations if water is present. And in fact, when we look at a couple of sample regions, we looked at a big highlands region and a big, mostly Maria region. And we looked at those big regions again to try to build up signal for this kind of test case. And when we look at our spectral slopes versus time of day, in the highlands region, we see a significant change in slope at around noon. And then it goes back up to the pre-noon, the morning slope values for the afternoon and evening. In the Maria we see a hint of that kind of variation, but it's not as statistically significant. And what we're interpreting this as is because these are higher slopes, redder slopes in the morning, and then they drop out at noon when the temperatures are highest, we're interpreting this as being in the early morning and then in the afternoon, the presence of water contributing to increased or redder slopes, and then a loss of water at around noontime. And we see, consistent with earlier infrared results, greater retention of hydration in the highlands region than the Mare region. And this is also consistent with lab results that have investigated cryosorption of water and thermodesorption. And so trends like this, where we now plot our spectral slopes for our highlands region versus temperature as measured by a diviner, this is what we would expect. It's consistent with adsorption and thermal desorption of water. And here we've broken up our big highlands region that I showed you before into a couple of different latitude bins. I'm not sure that the differences here are that significant, so I don't want to get into that too much, but we do see this strong drop off at the highest temperatures. And as I said, this is what we would expect for thermal desorption. So we can model these areas and these trends, relating the slope changes to basically, we can kind of pull out an estimate of activation energy, or in other words, how well the grains want to hang on to or retain the water grains, the water molecules for a given temperature. And so we're getting activation energies in around 1.2 to 1.3 EV for this region here, which again is what has been measured in the lab is a broad range, but that's consistent with what has been measured in the lab. And it also is consistent, I think, with what you might expect of lunar grains. And recalling that in the far UV, we're just looking at the very topmost grains, and that very fluffy top part of the regolith. We're just looking at the top grains, which are really going to be quite rough and space weathered, and so activation energies like this, I think, might be, you know, what could be expected. And then we can model the behavior, the spectral behavior, in terms of a thin layer of water molecules on top of a lunar regolith. And so we can model this in terms of the percent of a monolayer to see this change in slope that we see. And we find that what we're seeing is got to be you know, less than 1% of a monolayer. So very, you know, what we think we're seeing is something like 10 to the 12 molecules per square centimeter coming off of that top layer at around noon every day. And so, you know, here's our little cartoon of what we've imagined this looks like. And I wanted to just bring up, because I know that there's been this recent paper out about water detection using 6 microns, which is great. And we expect that those measurements are going to be sensing much deeper into the regolith than the LAMP measurements are. Because again, the LAMP measurements are only detecting those top grains. And I think that, that the 2 sets of observations ought to be pretty consistent. Because the SOFIA measurements are measuring deeper into the regolith and more water, and one can imagine that in such a porous regolith that there could be water in the porous regions that could be adsorbed. I know that those authors didn't consider adsorption and thermal desorption too much, but I think it's not out of the question and quite consistent with our LAMP results. So I just thought I'd bring that up as a conversation starter. And I think that's my last slide, Maria, so I'll hand it back to you. Oh, I'm sorry. What I also wanted to say is that, you know, now that we've done this test case, we're now looking all across the surface in smaller regions. It's still not super high res because we do need to build up our signal to noise, but we're looking all across the surface and looking for differences with terrain type and composition, for instance, and also ultimately wanting to compare with M cubed. Okay, so I'll leave it there.
Thank you so much, Amanda. Okay, we're going to move on to Norbert, who's going to talk about cold traps and ice storage on the moon. Take it away, Norbert.
Hello, yeah, I'm Norbert Schorghofer, and I work a lot on ices on planetary surfaces, the Mars, asteroids, and the moon. I think I have 2 other grants about ice on the moon, and I'm 1 other survey. So I do work a lot on ice on the moon. Next slide, please. And the oldest and still best theory about water, like macroscopic concentrations of ice on the moon, are cold traps, right? Which say areas are so cold that the sublimation rate, oh, not yet, I'm still on the previous slide here. Yeah, so at about 110 Kelvin, the sublimation rates are so low, or lower than we think the delivery rate is. And so that's still, you know, that's cold traps. And every map of cold traps which has been produced so far, except the one we published a few weeks ago, is based on just peak temperature criterion of 110 Kelvin or so. And all cold traps lie within permanently shaded regions. So this diagram here, which is perhaps too abstract, shows various concepts of ice storage. So there are permanently shaded regions which are not cold traps. In fact, about half of permanently shaded regions are not cold traps. And there are other storage processes. And we basically mapped all of them in a recent paper. Next slide, please. And so what we did, took this 11 years of Diviner data. So Diviner is the best, you know, is a great data, the best data set for surface temperatures on the moon. And we just included the time dependence, right? Because it's not the peak sublimation rate, it's the time integrated sublimation rate which matters. And so this cold traps should be defined by the average sublimation loss, not the peak sublimation loss. And so we divided the Diviner set into diurnal and seasonal bins. And seasonal temperature variations are important in the polar regions. And with season, I mean something called the draconic year, which is 347 days long. And so that gives us just, you know, cold trap map, which is based more closely defined by physics rather than this approximation of just using a peak temperature. Next slide, please. And so that's the new map of cold traps in the south polar regions. The cold traps are now 24% larger. 24% isn't such a large number, but as I explained it to my friends, this is expensive real estate. And next slide, please. Now, cold traps aren't the only storage ice sequestration mechanism which has been suggested. There's also, you know, something called the lunar ice pump, where you know, temporary temperature gradients can drive water molecules into the ground from surface molecules. That probably doesn't produce much ice, or doesn't sequester much ice, but it depends on grain size. So the larger the grain size, or the larger the pore spaces, the more efficient this process. And we made a new map of this too. So this happens outside the cold traps over areas which are 5 times larger than the cold traps. And so there's a new map of that too. Next slide, please. So another approach to using existing data to better understand where to expect water ice on the moon is to consider scales, spatial scales, which are finer than the resolution of orbital instruments, in particular Diviner, which, you know, gives us the temperatures which define cold traps, and that's, you know, that's roughly 100 meters or so. And so to do that, we used images just to get the extent of shadows, then used theoretical models to translate these instantaneous shadows to permanent shadows. We used the diviner temperature, studied them as a function of scales and Lola roughness and a lot of theory. And we made a model of the surface of a landscape at sub-resolution, which agrees at coarser resolution with the temperature as well as the shadow measurement. So this is sort of a big data synthesis project. And next slide, please. And which was published a few weeks ago in Nature Astronomy. And here is two histograms, one of permanent shadow regions, one of cold traps as a function of length scale. And the cold traps, the minimum size of a cold trap is given by lateral heat conduction, right? Limited by lateral heat conduction, which again depends on grain size. And at small grain size, you know, I call them out of this world thermal insulators. They're extremely, lunar dust is extremely good thermal insulator. So in terms of area, this sub-resolution cold traps is only 10% more area. And in terms of number, of course, the most cold traps are below the resolution of diviner. And so we are talking about billions of cold traps, each of which probably has eyes or should have some fraction of eyes. Most of them should have eyes. And the importance of that is, you know, in terms of emission target, if you have many of them, you know, we can land somewhere and pick one which is particularly favorable. Going to a large cold trap is a technical challenge. Going into a small cold trap where we have lots of choices to pick from and shorter distances, it's much easier. So in terms of exploration, that's an important implication. And next slide, please. And so yeah, so we analyzing data, and luckily we are not limited by the epidemic. We can just do this on our computers. We're analyzing lots of data, both at, you know, taking advantage of time dependence of the measurements, taking advantage of the resolution, basically the availability of data at many spatial scales, so we can extrapolate it to smaller scales. And there's much more to do. What I'm currently working on is apply these ideas to carbon dioxide cold traps. There are carbon dioxide cold traps on the moon. We have not produced a good map of them yet. So that's what I'm working on. And last slide, please. The first of these publications just appeared a few weeks ago. That's the time-dependent diviner data we used to produce many maps of ice storage processes. Then there is this Nature Astronomy paper, which also appeared a few weeks. I think the two papers happened to appear on the same day about the micro cold traps. And what I have not mentioned is we have also just finished a review article about the interaction of water molecules with the lunar surface. And that started with a workshop in Switzerland. And I should have listed all the co-authors here because most of them are involved with survey in one or the other way. And that's just been submitted to Space Science Reviews. Thank you.
Thank you so much, Norbert. Next slide, Amanda. Okay, it is now my pleasure to introduce to you Lynnae, who's going to talk about volcanism and venting on Ceres and the moon. Go ahead,
Sure,
Lynnae.
thank you. Sure, thank you so much, Maria. I'm Lynnae Quick from NASA's Goddard Space Flight Center, and you know, I just wanted to mention a couple of things before I got started on my slides in earnest. So I just wanted to emphasize how the work I do with TREX complements my other research and exploration roles, largely due to the work that I do with TREX, and because of the funding I've received for TREX, I've been able to be a science collaborator or an associate scientist on the DAWN mission, particularly for the DAWN at Ceres part of the mission and the extended mission and XM2 part of the mission. And I've also been able to extend my work from the outer solar system. I mostly study the icy moons, Europa, Titan, Triton, but I've also been able to extend my work to focus on the inner solar system, such as, of course, Ceres and the moon. And this extension allows for more overlap with my research group at NASA Goddard. Our lab head is Noah Petro, who is the project scientist for LRO. So TREX has really helped me integrate a lot better with with the goals of my the planetary geology, geophysics, and geochemistry group at Goddard. So next slide. Okay, so first I'll talk about venting on Ceres, and you'll see on the left-hand side of your screen, you see the spinning Ceres, and it's gonna pause right now at Akator. Oh, it didn't pause that much, but Akator crater, it's coming around once more, and there are two very distinct bright spots. Here it is, there they are. And so if we look at these pictures to the right of that spinning Ceres, those bright spots are Cerelia Thalus, which is this kind of dome, and Cerelia Facula is the bright deposit that lies on top of it. Beneath that, we have an image of the Venalia Faculae, which are just these another series of wispy bright spots on Ceres, and we weren't quite sure what they were when we received the data back from Don, but the thinking is that these are salt deposits, and what happened is we had brines erupt onto the surface in Ceres zero pressure surface environment. Of course, the aqueous part of the brine would sublimate, and then it would leave behind this lag deposits of salts. And so Don gravity data goes along with that theory. It revealed a low density region beneath Akator crater. And one thing that I was able to work with some Don team members on was just a theory hypothesizing that this region could be a partially crystallized brine reservoir. So if we just think of a subsurface pool of brines within the crust, or as I like to call it, a cryomagma chamber, because these brines are going to erupt at some point. And I was able to study that, and we'll go to the next slide, so I won't have to read all those words. I'll talk about it more specifically. One thing I did was consider that we had this brine reservoir, and I modeled the cooling and crystallization of this reservoir, assuming that it was filled with carbonate and chloride salts, and model its cooling and the changing in its composition as a function of time. And here it is on the top right. And you can see that depending on the temperature and the crystallization, the composition of the brines that would be pushed to the surface would change. And so what we're thinking is we have a reservoir, it has a fixed volume, and as these excess pressures due to cooling cause these fluids to erupt onto the surface. And what was really interesting, I did not cite the paper here, but you know, when we look at the compositions of the salts at Akator crater around Cerelia Thalus, which is this dome, it does look like we have the carbonate salts erupted first, and then as we gradually go out towards the dome, we have the chloride salts erupted. And so this was a paper that was published in 2019. And so we were excited about that result. The next thing that I did was, once I thought about, well, after we have these brine eruptions, what happens on the surface? And we can see at the bottom, looking at Cerelia Thalus on the bottom right, again, these brines are pushed to the surface, and they're probably very viscous, and they form this dome-like shape. And on the bottom right, I was able to model the formation of Cerelia Thalus as what I call a cryolava dome, using models that have been applied to model the formation of pancake domes on Venus and putative cryolava domes on Jupiter's moon Europa, and found that if this structure was produced as a result of extrusive cryovolcanism or these brine eruptions, whichever you prefer to call it, it could have been produced within 9 months, and you would have had very high viscosity, of course, salty fluids forming that dome that's underneath these bright spots. So we can go to the next slide. And secondly, I looked at the Venalia Faculae, which are on the left here, these wispy kind of deposits, and assume that in this case, venting is caused by the intersection of fractures with volatile rich fluid reservoirs. And we see this figure on the bottom left that kind of shows what's going on there, what we believe happened there. And so when these fractures intersect these volatile rich fluid reservoirs, again, we have fluids pushed to the surface because they are high in volatiles, and Ceres has a zero pressure surface environment. These particles follow ballistic trajectories. And so what we find is, with this venting, these halos that are produced, that are about this, that are the equivalent size of those of vanillin facula. It's really easy to produce those halos, assuming that we have less than 1% of any driving volatile, such as sulfur dioxide or carbon dioxide, that's driving this venting. And this was also modeled in Quick et al. 2019. An eruption source from a deep reservoir was recently confirmed in one of Carol Raymond's Nature papers that just recently came out, that is focused on the Dawn XM2 results. And so next slide, please. And so I focused on Ceres quite a bit. I'm getting to thinking about the moon now, working with a couple of folks, Dan Moriarty, Jake Richardson, Stephen Scheidt at Goddard, and Jose Hurtado at University of Texas, El Paso. And what we're looking at is Mayfic Mound, which is in the South Pole Aitken Basin. There's a lot of questions as to how Mayfic Mound would have formed. And so what we're trying to do is we're trying to use its composition, morphology, the gravitational signature and modeling to determine how this mound formed, if it may have been a volcanic dome. So we're hoping that it'll give us clues into the manifestations of impact basin related magnetism and provide context for upcoming missions. And we will go to the next slide, please. And so that's the work that I've worked on Ceres in the past, and I'm continuing to work on Ceres, and I'm just starting to work on the moon. And Norbert really set things up really great for this, when he mentioned the permanently shadowed region. So one thing that's of interest to me is when we think about ISRU and we think about these resources, we know that there's abundant ice in permanently shadowed regions, and that can possibly be used as a resource. But what about partially shadowed craters? What's the sublimation rate of ice in those craters? And could that be a resource depending on the sublimation rate? That's a question that I'm interested in answering. Also, when we look at Cerelia thalas again on the bottom on Ceres, Jennifer Scully, who's at JPL, recently came out with a paper that provides estimates for the volume of salt that we believe was extruded inside of Ceres Akator crater. And so we have estimates for the volume of salt. And one of my questions that I'd like to answer, and something that I'd like to model coming up, is can we work backwards from these numbers from the volume of salt to estimate to get better constraints on the volume of brines that were erupted to replace these salts. Remember, we're thinking that these bright deposits were brines that were erupted, and again, the liquid part sublimated and left this lag deposit. So if we can get back to working backwards, get back to the volume of brines that were erupted, that would provide reliable estimates on the rate of surface-subsurface exchange on Ceres at the time that these features formed, and we could refine models for the formation of Ahuna Mons, which everyone knows is Ceres' lonely cryovolcano, and also possibly Cerelia thalas. And I think that is all that I have. Thank you.
Great.
Thank you so much, Lynnae. Thank you. Amanda, next slide, please. Okay, so we have just 2 speakers left in theme 2, but we are running a little bit behind on time. So please try to stick to your time limit there. I know I haven't been enforcing that, but if you can, please. So Roger, sorry, it's not your fault that we're running behind, but go ahead, please. Roger's going to talk about mineral and water mapping with Tetracorder from rovers to M3. Go ahead, please.
Hi. So the title of this paper below it is TREX team and M3 team. So I have a paper in preparation. It actually started many years ago. The M3 team are all authors on the paper. So Carly will be seeing some things that she's seen before and some new stuff. Part of this came about because, well, Cassini took up a lot of my time after M3 did everything. And then for some of the mineral mapping, I didn't have the compute resources. So over the intervening years, I developed new compute resources with, we've continued to develop Tetracorder. And this year, I built a new machine that was able to finally handle the large M3 data set. So that's enabled new things to be studied. So next slide. So first, what is Tetracorder? So Tetracorder is a tool that has been in development while I was at the USGS, and I left the USGS in 2014 for PSI. And so it's got like 35 years of development by a team of expert spectroscopists. At times there were like 12 of us working on it. And it's different than other systems because it is used to identify things. Remote sensing typically talks about doing, you know, I'm lost for words here, you know, some index that might indicate something is, you know, a high probability of being there. Well, Tetracorder analyzes a very large spectral library, compares it to the observed data, and uses it to identify the materials that are present. And we split the spectrum up into many spectral regions. I'll discuss that in a minute. But we've applied Tetracorder all over the world, all over the solar system. So it has a lot of history in it. It's also being used on the Carnegie Mellon rover for theme 4, which I'll touch on. And then Eldar will, in the next session, will tell a lot more about that. Next slide. So spectroscopy analysis is pretty challenging because there are many problems with remote sensing doing spectroscopy. One, you have little tiny elemental substitutions can shift absorption bands, so you need lots of different example spectra. You know, it might be the same mineral, but slightly different chemistry, and the absorption bands are slightly different. But once we have that spectral library, we can do geochemistry. Scattering scrambles intensity information, and it causes a lot of problems. It makes it harder to derive abundances. There are different ways that the light interacts with the surface, from nonlinear to linear cases. And so nonlinear is intimate mixtures, molecular mixtures, and coatings. And then linear would be aerial mixtures. And Tetracorder handles all these cases through the spectral libraries. It's the tiny differences in the spectral features that are key. So it could be, you know, a small substitution will cause a small shift in an absorption band or a shape change, and we sense that. In some cases, there's changes in the shapes of spectral features with grain size that we can sense that are common for planetary regolith type grain sizes, and we exploit that and actually map grain sizes also, and I'll show an example of that. Let's see, I think I've covered most things here. So these tiny differences, which means you need very high signal to noise spectra or lots of average spectra together to determine things, you can get pretty precise in what you can derive. And that's how we've developed Tetracorder. Next slide. So we split the spectrum up into multiple spectral regions. Each spectral region has its strengths and weaknesses for sensing different absorption bands and the causes. So you know, you got the electronic absorptions in the UV and visible out to 1 to 2 microns. And then beyond that, you have vibrational absorptions. And we actually, you know, there's just, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, a dozen or so listed here. But some of these we split up into even smaller ranges, so that there's currently 22 spectral groups in the Tetracorder expert system. And then once something specific has been found, additional cases can be analyzed for like a ternary diagram or something like that. So there are currently 7 cases covering 22 spectral groups and 7 cases covering the 0.4 to 4 micron range. And that's to do that, we need a 25,000 line expert system with instructions on what to do to analyze the spectrum. And we're using currently 530 reference materials and 941 spectral features. And an advantage of this, the methodology here is compute time grows linearly with the number of things we put in. So we can add a lot more and still be able to do reasonable compute times. Next slide. So I'm going to first talk about the moon and then rover applications. And we all know that 3 instruments back in 2009 saw the 3 micron absorption in the lunar surface. And subsequently, there seems to be some confusion in the lunar community. There's OH and water signatures, both in the 3 micron region. They can be untangled, and they were untangled. So, you know, I'm not going to get into that, but, you know, if you want to have an email conversation offline, I'm happy to find to engage with that, because that needs to be clarified in the paper that we're writing. Next slide. So with the M-Cube data, I assembled it into a simple cylindrical cube for the global mapping data. It's 85 channels. And so the equatorial region sampling is 0.33 kilometers per pixel. So this is quite a large image cube. In order to analyze it, you need about 300 or so gigs of RAM to be able to work through it in a reasonable compute time. So I've run Tetracorder, the latest Tetracorder on it to look for all kinds, you know, phyllosilicates, iron oxides, and I've previously done the water, so we'll see some results next. Next slide. So there's 2 modes here that I did for the water and the hydroxyl. On the right here are reference spectra from the USGS Spectral Library, and it shows these are sampled to the M-Cube resolution and sampling. So there's 6 different OH band positions. Unfortunately, the spectral resolution of the M-Cube global mode isn't high enough to restrict the mineralogy that much. So for example, that bottom blue spectrum at 2.72 microns, there are many different types of minerals that can have an OH at that position. So while we can separate the positions of these things, it's difficult to assign a specific mineralogy. Then for the broader water absorption, in order to run Tetracorder on a spectral feature, I synthesized a spectral feature by reflecting the spectrum from the short wavelengths to the long wavelengths. So it's that gray zone in the right plot is the reflected shorter wavelengths. But this gives us a way to separate these subtle shapes between all these band positions that are basically at the same wavelength. Next slide. So here's the OH map that has been derived, and you see that the basically there's 2 different classes. The Highlands material has the OH band position at a longer wavelength. The Mare tend to have the OH band position at a shorter wavelength. I'm going to go through these fairly quickly. We can have an offline conversation or wait for the paper to come out next year. Next slide. Then the broader water position, again, we see that there's significant water in the Highlands materials. And as a side note, when I was doing this study, I tried to find terrestrial feldspars that didn't have any water and was not able to find any. I purchased and gathered dozens of feldspars and never found one that didn't have water. And pumping on a vacuum in the lab could not pull off the water. Notice that some of the Mare have water signatures also, but not all of them. There's also phase angle effects, and this gets into the diurnal activity. And one thing to note, and I did publish this in the supplemental material for the 2009 Cassini paper, is that with a diurnal effect, you also have a sun angle of incidence effect. And we'll discuss this in a bit, but even pyroxene band depths show a diurnal effect. So it's really a surface layer effect and an angle of solar incidence. Next slide. This is again water, just showing some more details, and the crater Copernicus, showing that it has water in part of the crater, but not all of the crater. And that's pretty interesting. We see a lot of craters that have excavated water from the subsurface. Next slide. So this is something new that the MCube team hasn't seen yet. Part of what I did in the newer Tetracorders is being able to use a curved continuum that adapts to the shape of the spectrum. And one of the problems with trying to detect water in the water band at 2 microns is pyroxene also has a band in this region, and the curvature of the pyroxene absorption caused a lot of false positives, so we could never separate the two. But now with the curved adaptive continuum, the pyroxene is taken out and we don't see it. And in fact, when you see the pyroxene band map, it doesn't correlate with this. Now, you know, the 3 micron feature is very weak, and the overtones, so 1.9 to 2.1 microns, is going to be very, very weak. Typically in the overtones is going to be 10 to 30 times weaker. And so we're really pushing signal to noise here. But let's see, I don't know, Amanda, if you can point to where Copernicus is. It's on the scale at the bottom, the red square called J, it's straight up from there, just a little above the equator, just go straight up. Yeah, so that's the Copernicus water being seen at 1.9 microns. Okay, next slide. Just another example of a small crater. This is on the far side, but it shows that a small crater has excavated water from the subsurface. So as a result, we see both endogenic and probable exogenic water on the moon. And that's a big conclusion of this paper that we're working on. Next slide. Now to some of the other minerals. So here's pyroxene. This is the 2 micron band position. And you see that there are phase effects here that I find kind of interesting, even with the pyroxene bands. And not only does the pyroxene band change in depth with phase, but you see some of the striping there, the different orbits are at different phase angles, which it means different incidence angles for the sun. And that the composition seems to change, so that this is saying that the very thin layer at the surface of the lunar soil is a different composition than just below it. And this is all in the optical surface. So in the top couple of millimeters. Next slide.
Roger, I hate to rush you, but we probably better move it along.
Yeah, I'm
Great.
Pretty close. Next slide. So a combination of the iron oxides and the Fe2+, which is mainly the pyroxenes and olivines. Go on to the next slide, which will be just the iron oxide detections. And I want to caution, the MCube instrument had a lot of scattered light. So there was a recent paper on detecting hematite, and the Tetracorder results are also showing similar, both hematite and goethite. But some of the scattered light issues with MCube are similar to the spectral features in the iron oxide. So I'm still cautious on this. I wouldn't bet my life on it at this point, but it's looking interesting. Next slide. Okay, so I've touched on some of these already, so we can skim over this quickly. Diurnal activity is also solar incidence, and that needs to be taken into account before anybody claims that things are moving around on the lunar surface. Let's see. Let's go on. You can check that out later. To the rover. So we have Tetracorder running on the Carnegie Mellon rover. This is Zoe, and Tetracorder is receiving data from an ASD field spectrometer, and it will be working to integrate other spectrometers too. But when a spectrum comes in, Tetracorder can analyze it in a fraction of a second. And this is an example of the output from a typical ASD spectrum. And you see that multiple things are found, and we haven't done any unmixing step, and that's because spectral features at different wavelengths have sense different things. So we can detect mixtures without having to do unmixing. Next step. So this is the final slide. So currently, well, our idea for rovers, and this has been done on the Mars rovers and stuff, is you map from orbit, you choose your landing sites, and you use some of the information that you've received from orbit to pick the landing site and pick initial areas where you're going to go through. But in the future, right now, when a rover takes data, it's got to send the data back to Earth, and scientists spend hours to days to analyze it. So the turnaround time for the rover to do something is very long. But if we have the science analysis on the rover doing real-time analysis, the rover can decide what to do next. It can analyze, oh, that's not an interesting spectrum. You can log it and send the data, the answers back, and even the data too, but continue on and wait until it finds something really interesting before stopping and contacting the science team. So we can, with tools like this that TREX is developing, the time for exploration is really cut short, so you can go to larger areas faster and do a much better exploration job. Okay.
Okay, great. Thank you.
Thank you. Yes, moving on to Becky. Becky, 10 minutes, please. Becky's going to talk about her results in looking at the grain size map.
Great, thanks. And Michael, are you here?
I think Michael is broadcasting from the Four Seasons.
Yes, that's the real Four Seasons behind me, as everybody knows. Yes. Hi.
Hi. Okay, great. So I'm going to save a couple of minutes for you at the end. So yeah, I'm Becky Ghent. I'm at PSI, talking to you from Portland, Oregon, and I am involved also on the Diviner Lunar Radiometer team, and I'm a co-I on Mars 2020 RIMFAX GPR, and I'm on another Survey team as well, and have a bunch of other projects, mostly on the moon. And Michael, you can see his participation here. He was on Cassini and a bunch of other projects. Specifically important for this, Michael is involved heavily in calibrating the giant Diviner thermal data set. And for that reason, I asked him for some help on the computational aspects of this project. So if you want to go to the next slide, Maria. So basically, my job here is to try to convert Diviner thermal measurements into an estimate of grain sizes on the surface of the moon. And I'm going to give you a high-level view of how we're doing this. So as I'm sure most of you are aware of by now, the Diviner nighttime temperatures specifically are very closely governed by the thermophysical properties of the materials that are radiating at night. And Josh Banfield in 2011 took advantage of the multispectral nature of the Diviner thermal instrument to calculate two quantities, which are the rock abundance and the temperature of the remaining material, which doesn't go into the rock index, which is, we call the rock-free regolith. So basically, he took advantage of the fact that when Diviner sees a field of view that contains a mixture of components, thermophysically speaking, on the moon, we can interpret those as being things like rocks that are very indurated and retain their heat through the lunar night because they have a high thermal inertia, and a thermophysically very different regolith component, which cools off much more quickly during the night. And that mixed, the radiance that you get from such a field of view that contains this mixture of components gives you an integrated radiance that is not a black body radiance curve as you would get from an all rock or an all regolith, so some component radiating at a single temperature material, but instead you can model that as a linear mixture of these components. So you can model it as a linear mixture of hot rocks and cooler regolith. And that enables the calculation of these two quantities. So on the left-hand side here, you see the familiar rock abundance map, which is a map that shows an estimate of the fraction of each pixel that is occupied by exposed rocks or anything that's thermophysically like a rock, high thermal inertia materials. And so you can see that young craters like Tycho down there at the bottom and the Maria, which have a lot of craters in them, really show high rock abundance values. For reference, the background regolith has an average value of rock abundance of something like 0.5%. So, you know, most of the regolith is not rocky at the surface. And then these higher, you know, rock abundance areas like Giordano Bruno Crater, for instance, has pixels that can exceed 50% rock abundance. And the other quantity, which is what we're going to use here, is the temperature of the leftover materials, so the temperature of the regolith. So assuming that we've accounted for all the rocks, we've subtracted the rocks out of the picture, this is the temperature of the remaining material. And we usually look at this in terms of relative values to a longitudinal average, because there's a latitudinal dependence of the temperature. And so we remove that dependence and we calculate this relative to the average. So on the right-hand side is a map of said regolith temperature, and that is actually our data to which we're comparing all of the models that we calculate. So this is already a derived quantity, and we can talk more about that later if we have time. So proceed to the next slide, please. So using this, Paul Hain and a bunch of others of us used those regolith temperatures in 2017 to calculate something that we call the H parameter, which is a proxy for thermal inertia. Thermal inertia on the moon and airless bodies is temperature dependent because we don't have the influence of the atmosphere to even out the, you know, the heat transfer. And so it's not quite as simple a task to think about what is the thermal inertia of materials on an airless body as it is on something like Mars, where it's a pretty familiar thing to do. But basically, it all boils down to this equation, which I've shown here, which is our model for how the density of the regolith, or the density of the regolith is a function of depth. So rho is density, and d is the density at rho sub d is basically the density at infinite depth, which for our purposes is somewhere around a meter. Rho sub s is the surface density, and h is this this E folding parameter that you know, communicates how that density, how fast it changes with depth. So the constraints for this, the reason that this model works is because, first of all, we have cores from Apollo, and we have diviner temperatures, which we can measure, to which we can match models. So we get a curve like the one shown on the left, and basically by running a one-dimensional thermal model and matching the nighttime predicted temperatures to the regolith temperatures that I showed in the previous slide, Paul and the rest of us made a map, which you can see here, of values of H in meters all over the moon. So a high H value means that you have very fluffy regolith, and a low H value means that you have less fluffy regolith, so higher density closer to the surface. This particular plot, I forgot to put the scale on here, but this is 0 to 10 centimeters. So the darkest points on this plot have H parameters of around 10 centimeters, and the brightest have basically, you know, 0. Okay, so this is the quantity, this H parameter map that we are basically adapting to calculate particle size. So the idea here is that well, I'll just say one other thing. The thermal model that we've used on the diviner team to produce this map does not have an explicit grain size dependence in its formulation of thermal conductivity. But we know that thermal conductivity does depend on grain size, and there are alternate expressions for thermal conductivity that explicitly do contain grain size. So what Michael and I have done is basically recast this model using an approximation to the thermal conductivity that does contain a grain size term. And we have assumed a single H parameter, which is the average H parameter over the whole surface of the moon. And we have instead calculated grain size instead of calculating H. So if you proceed to the next slide, you can see a little bit about how this goes. So these are some models that Michael has run. The curved lines in each case are thermal models, results of a thermal model that we've calculated for a particular latitude and longitude point, and a range of particle size values. So there's a parameter called chi that is related to grain size that we have tuned here. And the data points, the blue data points, are the band field at all surface temperature, nighttime derived temperatures. And so the procedure basically is that we run a whole suite of models for every latitude and longitude combination. And we then, for each pixel in the Diviner data set, which is a lot of pixels, we match the best fit grain size or the best fit chi parameter to the data for that pixel. So if you proceed to the next slide, ta-da, this is a preliminary result that is calculated at 32 pixels per degree. The Diviner data set are gridded at 128 pixels per degree, so it could potentially get better than this. But down at the bottom here, you can see our calculated grain sizes, particle sizes in microns for each pixel in this map. And I've overlain it here on the LROC WAC data set so that you can appreciate the geology. And we see that there are some interesting effects already showing up. And I'll say in the next slide some caveats to this, but first of all, we chose this area to lie over the boundary between the edge of the Aristarchus Plateau pyroclastic deposit, which is at the upper right, and the sort of background regolith, which is, southeast of, or southwest of that. So you can see that boundary pretty well, and you can definitely see that there's an average grain size difference between the pyroclastic region and the nominal regolith off that. And we can also see that there are some regions around the small impact craters in the regolith off the pyroclastic that show bigger grain sizes, which is what we would expect. Those little impact craters are excavating little rocks, and those should influence the average grain size. There is a caveat, which if you go to the next slide, Maria, I will point out, which is that we have not yet implemented the slope corrections that need to be implemented to account for things like what you can see in this picture here. So in this picture here, you can see an impact crater, and you can see that apparently there are different grain sizes on the walls. And in fact, those are temperature effects that show up when you have a non-flat surface. And we know how to deal with this. This is dealt with in the Diviner thermal model already, but it takes some computational work to integrate this into our solution, and that's what's going on right now. So Michael, would you like to just talk a little bit about the computational aspects of this? And just summarize, how big the data set is and where we are overall?
Yeah, so let me just mention something. We have an ongoing Diviner meeting today, and we actually discussed the slope correction to a certain degree, because first the old one was always stripy, yeah. And apparently Kaylin found a problem with that, and she found a better version. So we're going to have a meeting, splinter meeting, to implement that.
Let me just point out that she's my former undergrad.
Yes. Mm-hmm. Yes, so that's exciting, and the other thing is with this slope correction here, as you can see in the preliminary map, like you pointed out, the increase in particle size around the impacts, there's quite flat area, so there's good hope that the effect is real there, because there's no slope effect on the flat areas around the crater. And somebody today in the Diviner meeting also applied on a small field this slope correction, and sees thermal model effects also with inside the craters with the slope correction applied. So I think these, like you said, these effects are real. Computational wise, yes, it's quite challenging. We have 4 big data sets to go through pixel by pixel, 20 by 40,000 pixels. Too large for normal memory, even on our bigger machines. So you have to work with virtual arrays to dig through this data. But I found already some dumb, slow decisions that I did. well, first it was 350 years, then I was down to 50 years calculation time. Now I think it should be maybe 10 years or so on a normal computer. So, but we still need to go on a cluster to do it for the complete map in the highest 128 pixel by pixel resolution. The map that Becky showed took me 9.5 hours to calculate, simply because of all the thermal models to run. Even so, those you can pre-run, but then the processing through the very large 128 files, which are also have high dynamic pixel values. So yeah, it's a large data set. So it's a little bit of learning the data technology is the correct one, piece by piece, when we go along there.
And that's why we invited Michael to help us with this, because I do not have the capability to do, use modern programming techniques. Really, I think I ran some preliminary cases before we brought Michael on that took me forever as well, and they weren't as high resolution as what he's run. And the thing that really slows us down is just there's so much interaction with the data. There's so many, you just have to query the database over and over and over and over, and that's very slow. But I'm really pleased with what we're seeing here, and I think that in the foregoing presentations, there were many examples of applications, and I know that all of you are waiting for this map, and we're trying our best to get it out. But I think, looking at lobate scarps and looking at ejecta properties and, pyroclastic deposits, all of those things will be possible once we finish this. I should just say one final thing, which is that we can only go to 80 degrees north and south. So we can't do, super high latitude studies.
Yeah, even with a caveat that Paul Hain, who worked a lot with this model for the H-parameter map, he even thinks that the slope correction is difficult with at 60 latitudes, even north of that.
Yeah.
So we might have difficulties in creating realistic values.
That's right.
Out from 60.
You may have noticed that in Josh's regolith temperature map, there are a lot of empty pixels where the slopes exceeded some critical value that he deemed to be, past the point at which we could, with a one-dimensional thermal model, robustly model the radiation. So you get lots of self-radiation effects beyond that.
Thank you so much, Becky and Michael. I hate to cut you off. We're running behind time. Did you have one final thing to say? Sorry, Becky.
I was going to say that's all I have.
Great, perfect. Okay, so and Amanda has indicated here in the chat that since we are so behind on time, we're going to take questions in the chat, please. So if you do have questions, please do that and in the chat. And I think most of our speakers are looking at that to respond to you. So we'll just move straight on to theme 4.
Thanks so much, Maria, and all the moon people. This is really great and exciting results.